All right, welcome. Good morning. As I was introduced, I'm Michael Lorello. I am a electrical, computer, and systems engineer. I know that is a mouthful. What does that mean? It means when I went to college, I took classes that were around electrical engineering, so it's circuit design, but the computer systems portion of it also includes software. So I can do the electrical hardware, but I can also write the code that goes into the hardware. So I went to school at Rensselaer Polytechnic Institute. It's in Troy, New York. It's about 20 minutes outside of Albany. And got my career started in 1998. That was a while ago. Since then, I've been part of teams that have developed mail processing equipment. So this machine here takes sheets of paper, takes envelopes, folds the paper, stuffs it into the envelope, and then sends it out for you to get it received in your mailbox. Then I moved on to doing electronic door locks. So take your badge, present it, radio communication to the lock, tells you whether or not you can open the door and lets you in. Matter of fact, the locks on the building here, I had a part in helping design some of those there, like the bars that pull in automatically when you want to get into the front door. And now I'm working on aircraft lighting. So believe it or not, yes, there is software in some of those. This little guy here is what goes on the wingtips, and this flashes the white light, so that way it's for anti-collision, so other aircraft know the plane is around to help prevent collisions. So we do actually have software in here to regulate that flashing. So what I wanted to do first was start with the definition. So what is software? So software is instructions that tell a computer what to do. And I'll use the word computer generally, because think about a computer, you might be thinking about, a Chromebook or something you're writing term papers on or things like that. But a computer is technically anything that does any hardware that will execute steps of a process. So let's go into a little bit of technical jargon, because there's definitely a lot of terms, a lot of acronyms. Helps to always get familiar with that. So obviously computer, digital electronic machine. I grabbed a lot of this from Wikipedia. Digital electronic machine that can be programmed to carry out a sequence of arithmetic and logical operations, i.e. computation, automatically. So what is arithmetic? That's your standard math stuff, your addition, subtraction, multiply, divide. Then you have your logic, which is like an and, or, inverse, and those what we call binary or Boolean. So with those two sets of operations, we can pretty much do anything. So what is a program? Program is a set of instructions that's executed by that system. A process is a program being executed. You ever opened up like Task Manager on your computer and it says the list of processes? That's where that comes from. It's those lists of specialized programs that are doing certain things to let the computer operate. An algorithm, think of it like a recipe. You've got a set of steps you have to follow. It's a way to get from a start to an end product. That's your algorithm. And then code, or the act of coding, is the program or writing the program, and that can be implemented in any language. You guys are using Python, but there's many different languages. A bit, that's kind of like an atom. It's that lowest level. A bit is binary. It's either a 0 or a 1, or logic low, or false, or it's a 1, logic high or true. And then byte is a group of 8 bits. If you think back to like a computer system, you see something, oh, that's a 32-bit operating system or a 64-bit operating system. Things tend to be in powers of 2. And it's just because of the way the computer systems are set up, getting back to, again, binary. A bug, we all know what bugs are. They're annoying. But it's an error, it's a flaw, something that causes your program to not operate the way you expect or not work at all. And then we got a couple other terms like procedure, routine, subroutine, or function. What are all these? They're a smaller set of instructions. So you have your big program, and then you can break it into functions or subroutines. And that's where writing programs comes in, is you break it into these pieces, and we'll talk about that a little bit later. The video will do a little bit of trivia and history of computing devices. Go back to the 1600s. They were starting to get more into math and figuring out how all this stuff works. They needed a way to do these calculations a little bit more repeatedly with less errors, so they started developing tools. Here's a slide rule which calculated logarithms. You just slid the thing along and all the lines lined up, and that's what gave you your calculation. Didn't even need any batteries. A lot of mechanical parts, cams, levers, buttons. This is a cash register that actually calculated a total, and you put in another total and it would give you change. And that was all done using mechanical pieces. So then we started getting into electronic calculators as things like vacuum tubes and transistors were developed. So in 1945, they developed the Electronic Numerical Integrator and Computer, also known as ENIAC. Everyone ever heard of ENIAC? So it's a little tiny thing. 27 tons, 1,800 square feet, consumed 150 kilowatts of electricity. What did it do? It calculated the artillery trajectory. It took about 30 seconds to do it. That same set of calculations took a human over 20 hours. So that's where the benefit of this technology started to really show its true colors. Now, fast forward 50 years, and somebody implemented that same function on a microchip. A little bit smaller. So we're talking about big stuff here. Still kind of big in the 50s. That's a calculator built into the desk. Used relays, which are electromagnetic switches. You have a coil and a set of contacts. You energize the coil, it pulls the contact. That's what makes your connections. And so it had a series of those. Obviously, line powered. Couldn't do batteries for something like this. But a few years later, now we're starting to shrink things down because transistors are becoming more readily available, integrated circuits are becoming more readily available, technology is advancing, they're able to shrink it down. And then just a few years later, they finally got it pocket-sized. So where do you find computer systems? A lot of us tend to think big. Something like NASA. And lots of systems there, a lot of calculations. There you can see on the screen all the orbit calculations that are being done. And that's in the 60s. That's right now, that's 60 years ago this year. So fast forward now to 2016, things have evolved. Technology's gotten better, screens have gotten more fancy. You get the flat screens now, put a lot more information, a lot more computing power. Another area that you might consider is medical. Think about patient records, diagnostics, all this information, your charts. You ever seen the doctor pull out their chart and it's like this thick? That's all information that's specific just to you. Now imagine that times every patient they've got. So there's systems that were developed to try and manage all that, or if they're trying to look up symptoms to try and diagnose a disease. You've got old systems like this here that all those big reels, those were tape drives. So magnetic tape, that stored all the data. So those disks would whir around and pull the data out, and that was how you looked up stuff. Now, let's relate it a little more to what you guys are used to now. Think social media. So you post something, you look at somebody's stream, you're scrolling through looking for memes. Where is all that information? Where is all that data? How is all that data being served up to you at the swipe or stroke of a keyboard? These big server rooms. This is from 2016. That's a Facebook data center server room. Just racks and racks of high-speed computers and hard drives, just storing terabytes of data served up to you at the swipe of a finger. Let's get into your own home. Where can you find stuff that has software on it? Alarm systems, home electronic assistants. Think about it. Alexa, tell me a joke, or hey Google. Voice commands now. It's all done. That's all software. Smart TVs, game systems, mobile phones. Think about it. It's like we have more computing power in our pockets now than was used to send people to the moon. Toothbrushes. Some of the electronic toothbrushes, they'll tell you how long to brush for, if you're brushing too hard, when the bristles are worn out. It's all software. DVD players, cars. I forget, it was a few years ago, I think BMW was touting that they had like 87 microcontrollers in just a single car. Let's just look at one room, the kitchen. Microwave oven. One button, hit button for popcorn. It knows how long to run and how strong to run the microwave. Some of the air fryers. I mean, just look at the input on there. You've got buttons, you've got display. You just hit a single button and it can cook automatically. How is that done? That process was analyzed. They figured out what that recipe was, that algorithm, programmed it in. So the user interface is very simple. Refrigerators. Dishwashers, they can automatically, it used to be mechanical timers, now they're automatic sensing. They can tell when the water's clean enough to know the cycle's done. Let's look at other stuff in medical, like imaging systems. You know, think about all that data that's being collected from the patient here, and they can put together an image to look inside the body and look at, let's say, I'm gonna guess they're probably looking at the horse's joints to see if they have a problem with their joints. You can see that now. It used to be you'd have to actually go in surgically. Now you can do it all in imaging and see a lot more. Prosthetics. You know, think about, somebody's got a stump of an arm and they can actually put sensors on there, tell when they're trying to move a muscle that used to be there, and actually drive motors now to mimic that movement. AEDs, automatic external defibrillators. You know, we have a company right in town that designs those, DefibTech. So let's get into the basic building blocks. So when we talk about software, we're getting into what does it run on? It runs on the hardware. What is the hardware composed of? Typically CPU, central processing unit. What is that usually composed of? It's memory, read-only, writable. The read-only might be where you actually store your program. You don't want that to get messed with. And then you have your writable, which would be your kind of your scratch pad, make a variable and change it. That's where you put that information. They have registers, kind of similar thing. They're these little areas that you can put data in and then you can pull data out, you can change it. You can do those arithmetic and logic operations to them. With timers, if you want to keep track of time, you want to do a delay. I think it was in Python, is a delay or sleep. That's where timers come in handy. We use the timers for those lights. We want to blink 250 milliseconds and then wait 1,000 milliseconds. We use the timers for that. So the ALU, arithmetic logic unit, that's the heart. That is the heart of the CPU. And what is it? It's this magical block. And you have inputs and outputs. So you have operands, so that would be where you're going to put your information coming in, something you're going to use, something you're going to operate on. You have status inputs, you have opcodes. Opcodes are your commands. And then what happens inside this is it produces a result and a status. So let's say it subtracts two numbers and the output is 0. Status bit is going to have a status, registers are going to have a flag in there for 0. It'll turn 1, binary. Let you know, hey, the output was 0. And you can use that for making decisions. So the operations that it performs, like I just said, it'll do the add, subtract, increment, decrement, negate. They typically have a fixed bit. I was talking earlier about, you look at your computer systems, 64, 128-bit, 32-bit. They tend to be those powers of 2. And it's just because everything's binary. It's just how many bits wide they want to make these things. So the code we write is translated into these streams of instructions. When you think about it, you write this Python program, you want to print a sentence, hello world, and then you want to go back and set a variable and increment the variable. When we write that code, we have to translate that into these low-level instructions. We don't have to do it anymore. Now we have specialized programs that can do that for us. But back when these systems first came out, that was all done manually. And that's where these levels of code are. So if we go down to the lowest level of code, we have that CPU with the ALU. It's processing these streams of instructions. We read the instruction. We take in any of the relevant data, or we point to a register. We perform the operation on it. Then we take that output and we do something with it. Either put it into memory, put it into another register. So when we talk about that level of operation, we're talking about machine code or machine language. I don't know about you, but I don't know what that means. I don't understand that. It's a stream of numbers. The machine knows what that is. It knows what to do with it. So this, what you're looking at here, is called hexadecimal. So that's base 16. So we're used to in math, we're dealing with base 10, 0 through 9. Base 16 is 0 through 9, and then A, B, C, D, E, F. And that's, again, we're getting back to powers of 2. 2 to the 4th is 16. This code is broken up into opcodes and operands. So opcodes are going to be the actual instructions. Operands would be what your arguments are, whether it's variable, register, location, and memory. And that stream, because it's really hard to interpret, we need to take it up a level, because otherwise it just gets ugly. Because when they used to program these things, they would do these even as far as like pressing levers and turning knobs. So imagine punching all that stuff in manually, and then you fat finger something and mess it up. You have to go back and redo the whole thing over again. So when you start getting into bigger programs, that gets really unruly really fast. So what they used to do is they would use ways to store that. And you'd see punch cards or punch tape. So basically what that's doing is those holes are going to correspond to these values, and then the machine can read it in. And now you're reading it in the same way every time. So if you write a program, you can then bring that in and have repeatable results. So if we take it up a step now, we go to assembly language. So assembly language, it's a structured language. It's easier to read. You're starting to incorporate more symbols and pieces of information that humans can understand a little bit better. You structure it, so you actually start to have, you can put things into functions and groups of instructions. So for example, this is a section of code. It's written in microchip PIC assembly. So microchip PIC is a brand of microcontroller. And it has mnemonics and operands, has labels and directives. So think about what these are. Labels are to help you identify sections of the code. Directives would be special things that the assembly translator, called an assembler, would need to know that you're compiling it a certain way for a certain brand of micro. And then you have the mnemonics and operands, which is that kind of English translation of that machine code. So you look at these commands like movef, XOR LW. These are mnemonics that you can get off, let's say, the data sheet for the microcontroller. So if we look at movef, what is movef? Movef is going to move a value from one location to another. Or exclusive OR. That's going to take a literal value. In this case here, you see the XORL 250. It's going to take the number 250, and it's going to exclusive OR it with the contents of register W. And then that result is state stored in W. So you take all this stuff and you put it all together, and that's what's going to help build your code. Now, assembly, I used that years and years ago. I haven't written assembly code, and I can't tell you how long. But it was when we needed to do stuff that was really tight in terms of timing, or you just didn't have the luxury of space. You know, you had a small microcontroller, didn't have a lot of memory, you had to make your instructions real tight. So you would write it in assembly to do that. Now, let's take up a step into the higher languages. This is what you're used to. So C, C++, Java, basic Python. These are interpreted or compiled languages. So what's the difference? An interpreted language, like Python or BASIC, the computer system interprets each line as it goes. So here's a program that I wrote probably, I don't know how many years ago, probably about 40 years ago, on a Commodore 64. Simple thing, prints the word hello, and then it prints the number 1, 2, 3, 4, 5, and then it goes back and cycles again. One line at a time. If I have a mistake, like I typed the word next wrong, it'll write down, it'll print hello, it'll print the number 1, and then it'll say syntax error. But it got down to that point before it actually realized there was an error. The same thing I believe in Python, right? You have a bug like partway through your code, you'll get partway through and then it'll throw an error. So that's because it's interpreting it as it goes. Now, there's a slight difference with languages like C, C++. Those are compiled languages. So what you do is you'll write the whole program in, let's say, a text editor, and then you'll run a special program called a compiler. What does the compiler do? It translates what you wrote into the machine language. And what that helps do is it makes it more portable, because now with a slight library change, you can say, I want to point to a special library that is made for Mac, or that's made for Microsoft, or that's made for Microchip, or Samsung, a different brand of microcontrollers. The language, the program that you wrote is more portable, because now you don't have to change that. You just change a couple of library files and you're done. It makes life a lot easier when you're trying to expand to more than one platform. So C, this is that same program that prints hello and then prints the numbers 1 through 5. It's just written in C. So we have that while 1, that's our infinite loop, that go to 10, it's the same thing as doing that while 1. We print hello. We then do a for loop that prints the number 1 through 5. And then of course you got just I took a little snapshot there of Python just to kind of show the differences, but it's that basic structure of, depending on which language you're doing, is going to be relatively the same. It's there. It's once you have the basics of one, to learn another one is not that bad, because you're building on the foundation of the concepts of algorithm development. And so that's where we'll kind of get into now. So I know all this stuff seems really complicated, but there was a saying, how do you eat an elephant? One bite at a time. Yes, I know, geek joke, I couldn't resist. So what does the creation of a program involve? There's usually several tasks. You've got analysis. You're trying to figure out what are your desired outputs. What are you trying to get done? What's the process? How do we do it? What's the algorithm? What's the algorithm we're going to use? What are the inputs? What's the ingredients that are going to go into this? Then we'll generate the algorithms. We'll figure out how to do it. There might be more than one way to do it. That's okay. We'll determine our resources. We're going to do something that's going to require a lot of number crunching. We may need a lot of memory. So we'll figure that out. How fast you need to get it done. So think of that software program. You got a box. You got your inputs. You got your outputs. Let's take an actual example. So this is something you've probably seen, just around. You've got, or matter of fact, I believe the Guilford police cars actually use the wheel and lights. So there's an issue with lighting. You ever come across that, especially at nighttime, and there's an accident or a broken down car, and there's just the lights are flashing on the emergency vehicles, and it's blinding. It's very distracting. Imagine trying to drive past that. It's potentially hazardous. So how do we fix that? There's a problem. How do we solve it? Let's break down the requirements. What should the flash patterns be in the different modes that the vehicles can operate in? What are some of those modes? We're driving, we're in pursuit, we're stopped, daytime versus nighttime. How do we detect those modes? So we know what the modes are, but how do we detect them? All right, let's break that down. We can use vehicle computer feedback. Computers are in the cars now. They'll tell it how fast it's going, what gear it's in. There might be light sensors for the dashboard. I don't know if you've seen some of the cars that the dashboard will automatically dim or get brighter depending on if it's light or dark out. They have light sensors. All that information is available right in the computer now. We can tap into that, and our lighting control system can use that information. We'll know what the vehicle speed is. We'll know what the light sensing, proximity to other vehicles. One of the features that our lighting system has is when two cars pull up next to each other, the lights will automatically synchronize. So that way you're not getting this chaotic barrage of random lights. If you look closely, if it's a wheel and light system, you'll actually see they may actually be synchronized perfectly with each other. And they do that by knowing that the cars are next to each other. What's the user input going to be? Probably keypad, switches, maybe a computer connection. If we have different modes, different fire departments or police departments in different states or even in different countries may have different siren sounds or light patterns. We want to have the same hardware. We don't have to have different hardware for everybody or write special software for them. So we'll make it configurable. You can actually download flash patterns. So we'll put a computer connection in there so you can connect it up and then let the users load up their stuff. And then what's the user output? Obviously the lights and siren. So now let's actually develop the solution. So we've kind of scoped it out now. We know what we have to do and how we want to do it. Got to figure out how big can the system be. We are talking about an emergency vehicle here. We're not talking about ENIAC. We're not going to put this in a room. It's got to be portable. It's got to be small. Something like that. It's about that big. It fits in either the trunk of the car. They might even be able to fit it under the seats of a larger vehicle. How many buttons? Remember, you've got somebody, the person that's going to operate this is going to be driving the vehicle as well. You don't want to have a full-size keyboard that's going to be crazy and have to go type commands in. That's going to be dangerous to have them do that. So let's try and keep it simple. Maybe just a simple set of keys, a couple levers, maybe a knob. So this is when the electrical and mechanical software engineering teams all work together and figure it out. Mechanical team will figure out how to make the case. Electrical team, how to design it to make the buttons and the lights work. And then the software team will figure out how to drive everything. We'll break down that function, each function, into those bite-sized bits. Do the flash patterns. Maybe you have multiple teams working on this. Okay, you guys are going to work on the flash patterns. You guys are going to work on the button inputs. How about the sensing? Processing the messages coming in from the car. Figure out what we're going to do with it. Button functions. We'll develop those algorithms. How do we program the flash patterns? How is it going to use the information coming in? What will each button do? Is each button going to have multiple functions or is it going to be dedicated functions? What do the lights do in each mode? So when we look at this problem now, we're going to use some different development tools. Who's heard of a flowchart? Okay, very popular tool. What does it do? It helps visualize what the program wants to do. It helps you see what variables you're going to need, what decisions you're going to have to make. You can kind of run through it and see, does this make sense? Or do you maybe find a flaw in your algorithm and say, wait a minute, oh, I've got a condition here that's going to put me somewhere I don't want to be. So now you can fine tune it. You can say, oh, maybe I need another decision point here to know if I'm allowed to go down this path. So that's where flowcharts come in handy. We can identify this information. That helps us build our algorithm. Might write pseudocode, which is kind of that mix of human readable and actual code. You're just, once again, you're trying to fine tune your algorithm, figure out how you want to implement this. Here's an example here of, I'm going to read the sensors. Don't know how I'm going to do it yet. I know I'm going to read the sensors. If the gear shift sensor is in park, I'm going to have a flag that's flash mode equals slow. If not, flash mode equals fast. You start putting this together to figure out how you're going to actually write the code. So when we start thinking about careers in software development, the field is very broad. I mean, that's just a handful that I came up off the top of my head. You've got web page design, network security, forensics. Think about a criminal that tries to wipe their computer of evidence. There are people that are trained to go in there and figure out how to extract that information and rebuild it off of a hard drive that's been erased. Manufacturing automation. You think about these complex manufacturing systems. A lot of them have what they call PLCs, programmable logic controllers. They're little boxes that you bring sensors and control motors with. And there's, once again, it's an algorithm, it's logic, it's making decisions. I'm going to move the manufacturing line belt to here. I'm going to bring in a robot arm to screw the cap onto a bottle of Coke after the bottle's been filled, and then I'm going to move it on. That's all done using these controllers. Embedded systems. Most of the stuff I showed you earlier, the appliances, the equipment, that's typically what they call embedded systems. So it's hardware that's very tightly tied to the software that's running on it. You may also refer to that as firmware. And then, of course, computer applications, your mobile phone apps, your word processors, video games. So those tend to be more purely just software. Options are flexible. A lot of people work individually. Mostly work as part of a team, especially when you start getting into these bigger software projects. What are some of the skills that you either want to have or be able to develop, or be open to learning? You definitely want to be open-minded. Communication is a big one. You're trying to communicate ideas, share ideas. Hey, I've got an idea how to do this flash pattern. What do you think here? And you share those ideas, and that's where people can kind of throw darts at it and figure out, okay, well, oh, if you have this condition, well, that'll break it. So you work all that stuff out before you start writing the code. Patience. I can't tell you how many times there's been issues with bugs that have been very frustrating. There was one situation back when I was at the mailing machine company. They were designing a new printhead that would print the postage on the envelope, and it was using an inkjet technology. The software engineer was trying to get the printheads to work, and she burned up probably 2 or 3 printheads. They would just, she'd start the code and it would just, you'd see ink spray out and then the thing would just blister. It would just fry the head. So long story short, she finally found the error. She had been writing in assembly code and she had a 7 instead of a 1. So one of the bits was staying high and leaving the heater on for the head. It was cooked like 3 or 4 heads before she found it. There was some colorful language that I heard her say before when she finally realized that. But happy to say, fixed it and got the system working. Definitely want to be able to give and receive constructive criticism, especially when you're doing peer reviews, going through the code. Hey, I got my, here's my user interface for the light configuration system. What do you think? People run through it, say, the buttons are a little small, hard to get, I keep mishitting it. So you can feed that stuff back so that way improvements can be made before it actually gets out to the paying customers. Empathy, somebody's having a tough time with it. You want to be able to kind of relate to them, work with them. You definitely don't want to be kind of a combative atmosphere. You want to be supportive because that's the key stuff. Logical, analytical thinking. These are like big puzzles. You're trying to put something together and get to a solution. And problem solving. And then self-teaching, learning a new language or learning a new way of doing things. So you might be asking, is software development for me? And so some questions you could ask, do you like to solve problems? Do you find it interesting to break problems into tasks down into small pieces? Do you like playing video games? Do you envision yourself maybe making games one day? Do you like working with data? Do you like considering, do you consider it a kind of a puzzle? And do you use programs and wonder how they work or what it takes to write them, or it's like, what, I don't like the way they did this. If I did this, I would do it that way instead. And you start kind of poking at other things. You're finding that ways to improve them. So that's all I got. Any questions? I know it's early. Well, thank you. Thank you so much for having me, and I hope you learned a little bit, got a little bit more clarity as to the world of software and software engineering. It's definitely an interesting field, and there's a lot of availability there. I did throw it to that's some of my sources. So I did some research and did it all. Didn't have to go to the library and use the Dewey Decimal System or card catalog or encyclopedias now. Able to use our technology and software and do it all right from here. All right, thank you.